All right, lesson number 9 in Unit 2 continues our look at related rates problems. I want to do this for a few days because I want to drive home the pattern. I want to hit the rhythm on how these problems work so that you know what you're getting into when you get into it. I want to do 2 in this video. It's a short one because really I want you to focus on actually doing this stuff yourself. So here's our example. It's example 4 because examples 1 through 3 were in the day 8 video. A hot air balloon is rising vertically. An observer is 1,000 feet away from the point on the ground directly below the balloon. When the balloon is 500 feet high, the rate at which the angle of elevation is changing is 0.25 radians per minute. How fast is the balloon rising at that moment? You've got your hot air balloon. It's above ground. You've got guy on the ground looking up at the balloon. This is your angle of elevation. This height is changing. But this distance is always 1,000 feet. And it's always 1,000 feet because the balloon is always rising vertically. So, what do I know? I know that the angle is changing at 0.25 radians per minute when the balloon is 500 feet high. I want to know how fast the height is changing at that moment. I know about theta. I want to know about h, so I need something that relates theta and h. So I'm looking at something that relates theta and h and maybe a number, and that looks like it's some kind of tangent problem. So I know that the tangent of theta is opposite over adjacent. Or if you like, h is 1,000 tan theta. Again, notice, just pausing, how this goes. We draw a picture. We talk about what we know. We talk about what we want to know. And then we relate the thing we know about to the thing we want to know about. And we do that using tangent in this case. If we knew about 2 sides and wanted to know about the 3rd side, if angles weren't in play, I'd use Pythagorean theorem. But I'm going to use trig. What happens now? We take the derivatives of both sides with respect to time. The derivative of h with respect to time, that's easy. That's the guy we're looking for. On the other side, the derivative of tangent theta is secant squared theta times, by chain rule, d theta dt. So what's left for me to know? I have to know what d theta dt is. That's easy. And I have to know what secant squared theta is. So I have to imagine a right triangle at this particular moment in time. At this one moment in time. So we've got that, and then your hypotenuse. Let's see, this is a 1, 2 radical 5. That's 500 radical 5. It's a 1, 2 radical 5 right triangle. So that's 500 radical 5 on the hypotenuse. So secant is hypotenuse over adjacent. Hypotenuse over adjacent is radical 5 over 2, and we square that because that's squared. So what does that turn out to be? Turns out to be 625 halves feet per minute. We measured height in feet. We measured time in minutes. So dH dt is in feet per minute. We double check. Our answer is positive. We expected a positive answer because the height of the balloon is increasing, and we know we're in good shape. That's the thing we were supposed to find. That's the thing we found. All right, one more. This is a classic problem. I wanted to show a couple of classic problems. Water runs into a conical tank at 9 cubic feet per minute. Conical tank. Picture. The height of the tank is 10 feet, and the base radius is 5 feet. How fast is the water level rising when the height of the water is 6 feet? So what have I got here? I've got water in the tank. The water forms, I suppose, a water cone. It's got a base radius that is changing. It's got a height that is changing. And so what do we have? Blue for water. I like that. We know this thing. We know that the derivative of volume with respect to time is 9. That's just somebody turns on the spigot, water is always flowing in at 9 cubic feet per minute. What we want is how fast the height of the water is rising when the height is 6. So I need some equation that's going to relate what I know to what I want to know. And so I'm thinking the volume of a cone is 1/3 pi r squared height. Now here's the problem with that. I don't have anything that connects volume to radius. I kind of need radius out of there. I want to connect volume to height, not volume to radius. So here's the thought, and I'll just throw this out there. This triangle is a right triangle. This triangle is a right triangle. And they share an angle. They're both right triangles. Those two triangles are similar. Their sides are in proportion. And so R can easily be replaced by half of height. Not only is the base radius half of the height of the whole cone, but as the water cone grows, its radius is always half of its height. And so I can rewrite this as 1/3 pi 1/2 h squared times h. Or if you like, pi over 12 h cubed. Now our problem is much more doable. Looking for the derivative of velocity with respect looking for the derivative of volume with respect to time. The derivative of volume with respect to time is the derivative of this thing with respect to time, and that 3 comes down in front, gets multiplied by the pi over 12. That's pi over 4. Power decreases by 1, and then we multiply by the derivative of height with respect to time. So now we just plug everybody in. 9 is equal to pi over 4. The moment in time where we're interested is h equals 6 times dh dt. And solving from there is very straightforward. dH dt is 1 over pi feet per minute. We measured height in feet. We measured time in minutes. So dH dt is 1 over pi feet per minute. What I am hoping you are driving home with yourself is whenever you see one rate that affects another rate, two related rates, you are establishing a relationship between the thing you know about and the thing you don't know about for the purposes of differentiating and substituting to solve. So that's my hope. I hope you're nailing this thing. We'll look at it for another day in class and then one more beyond that. And that is all she wrote. Thanks, guys.